So I am Mike Berg, and welcome everyone. I hope everyone's having a great day. We're going to talk a little bit today about connected control cabinet and the increase in networking going on in those connected control cabinets. So today's presentation is a primer on physical network architectures and best practices within your control cabinets. And my goal with the conversation is to review the elements of the physical network architecture and recognize some of the strategies that you can use to deal with the key challenges, such as environmental conditions, as well as methods that you can use to ensure a more reliable installation and ease your troubleshooting and upgrading systems once they're at the end site. So let's get started. All right, so this is my little icebreaker slide here, and it's all about high performance equipment working its best. So I want you to consider a little scenario. Let's say things turn in your favor and you're able to afford any car you want, and you go out and get that car. Let's say it's either a Ferrari or maybe a Lamborghini or maybe even a Tesla. What's one of the first things you'll want to do once you get that car? You'll want to test it out. You want to see what it can do, right? And to do it, you're going to have to find the right stretch of road, one where you can really open it up and really see what that car can do, or see what that high performance equipment can do. So if you were in this scenario, which road would you pick? Would you pick the one on the right with smooth curves that you can see accelerating down that road, or would you pick the one on the left with ruts and gravel and who knows what's down there, down that second path? So I think you kind of see where I'm going. You are all out there and you're specifying the highest performing electronics, so the PLCs, the managed network switches, servos, wireless equipment, even power over Ethernet equipment, and it's all coming down on the plant floor, and it's often terminated in the control cabinet. All this equipment, they are like the Ferraris, right? And today's conversation is about how you can build that smooth road and how you can take out the barriers and make it so you have a road where you don't have to slow down, where you can really leverage the capabilities of the equipment that you're putting in there. And so you can maximize that gear and what it can deliver. All right. So there's a stat out there that something like 85% of the new control devices put into control panels are Ethernet enabled. I think that's pretty accurate, or it's pretty close to it. So there's a real transformation going on inside control cabinets. It's changing design strategies, and it's simplifying things in some respects, but it's also raising some critical factors that we need to address as well. Some of those things we'll cover today, and they include things like space optimization and organization in the panel. And that's planning for what types of network devices and power devices are going to be in that panel and where we're going to put them, and how to maximize the space within the cabinet so that we can implement better performing designs. Related to this is also EMI noise, right? The enemy of a good signal is EMI noise. So we have to find ways to mitigate it within the panel using defense in depth strategies, grounding and bonding, shielded devices. The more obvious thing is actually planning for the right device cabling for the network. What's the media? What's the right design so that it's best suited for performance and reliability and the environments that we're putting them in, and ensuring the control standards and safety regulations are met. And considering also, how is this panel going to be used, this machine going to be used? Where is it going to connect to the wider plant network? And how can we help ensure there's reliability and minimal commissioning time for that panel? The final two things, and I probably should have put these earlier on, it's around addressing safety. So you've got network equipment out on the plant floor. There's an increased need for IT personnel and others that may not have safety protocol or safety equipment that need to access certain network equipment. So we need to have a good strategy for how we're going to deal with safety and with access control and security. Okay, so I'm going to start out talking about some standards with industrial architectures that apply to the physical network. So from a telecom perspective, industrial networks at the top of the network can be very much like enterprise IT networks. But as we get further down into the network and we get more closer to the field and device level, the more dynamic the environmental conditions become, and there's additional factors that we have to consider from the physical network perspective. So what we're showing you here is the industrial standard TIA 1005-A. And it gives a guiding premises standard that references both the architecture, and that architecture supports almost all the industrial topologies that you're seeing out there today. And it also addresses the environmental aspects. So as you get further down into that network, you've got a method to address the environmental factors that are going on. And so on the left-hand side, we show that architecture from top to bottom and the influence of M.I.C.E, or the environmental factors. On the right-hand side, we're showing a table that you can actually use to evaluate the spaces on the plant floor, where equipment's going to go or where cabling is going to run, and the harshness of that environment across different environmental factors. And those include mechanical factors such as shock and vibration, ingress factors, water and dust ingress, climate and chemical, so the environmental conditions with temperature, and then also anything corrosive, and then electromagnetic, or the noise factors going on in the space. So they're common things that you would plan for, and it just puts a methodology and an acronym to it. So as we're evaluating the spaces, we can evaluate, are they more office-like, are they harsher, are they more industrial-like, using this scale. Okay, so this is a closer look at that universal TIA model. And TIA, by the way, stands for Telecommunications Industry Association. And the model on the left is from TIA 1005, and it is used for naming the parts of the network cabling system. If we start conceptually at the bottom of this diagram, it starts where it says EO, and EO stands for the equipment outlet. There are 2 and sometimes 3 set of patching systems or distributors on the way up the network to the top, and that's where you see DA, DB, DC. In your office, if you're sitting in your office today, the topology that is shown here is actually similar to how your network is connected, except at the very bottom you would have a TO for a telecom outlet, or where your computer is plugged in, whereas in this diagram it is EO. If we look at the different distributors, the DA, DB, DC, these can also be familiar. A DA is also an access switch. So DA is the access level network switch. A DB is the distribution level switch. And a DC would be considered the core switch, or something more likely to be in an enterprise data center. If you look at the diagram, there are different topologies that you can integrate. Home run versus network segmentation is all possible in these topologies. The cabling systems that are shown here are by the lines also start at the bottom, and they move upward toward the network core. So the links that connect the equipment outlet is called cabling subsystem 1. Then moving up between access layer and distribution layer is subsystem 2. And then attaching to the core is subsystem 3. So note that in each one of those segments, both copper and fiber can be used. Fiber is often used in levels 3 and 2, and copper is more common in levels 1. Okay, so we show you a diagram here showing you the cabling and showing you that access layer. All right, and so as I mentioned earlier, many Ethernet devices are now present at this bottom layer of the network. In fact, the largest concentration of devices is going to be down here at this layer 0, layer 1. And so the need for these connections that are coming back to the control panel are present at the field level as well. So you've got I/O sensor connections, you've got smart blocks using network connectivity to connect, and you've got hardened switches, cameras, and other devices that are leveraging the network and then coming back and terminating into a control panel. So even those devices out in the field, they're coming back and they're connecting into the control panel, and the channel evaluation becomes part of what you do in the control panel. So the architecture provides us a way to plan for the cabling infrastructure, and us as manufacturers, we build products to the standards and to meet those environmental conditions. And down at that field level, there'll be common connectors and components such as an M12X code, which mates up with a 4-pair Ethernet cable, and an M12D code, which mates up with a 2-pair Ethernet cable or a sensor cable. So following the TIA architecture better enables the system to be testable all the way out to the edge and to that last device. And it's going to give you confidence that the panel built will perform in the plant floor network as you designed it for plant floors that use the same architecture. So now we'll take a look at some of the solutions working down the topology of TIA. So if you're at the higher levels of the network, you are more office-like, and there are not going to be as many environmental ratings required. It's going to be more of an office setting. It's typically going to be a higher bandwidth need because you're in the backbone of the network, and it's likely going to be solid copper cable construction or fiber optic cabling connecting these parts of the network. You're going to have typical components used in a commercial environment used in this space as well. So you will have category 5E and category 6A jacks. You may sometimes have shielded twisted pair and sometimes have unshielded twisted pair. There will be patch cords used in this network. Typically, they'll be category 6 or 6A, and they'll be either shielded or unshielded. And you'll also have cable connections being made. And these will be category 6 or 6A, and they can be UTP as well. Moving down closer to where the control panel is, this is in the cabling systems 1 and 2. You're more likely to have these M.I.C.E factors come into play. So you have a harsher environment, and this is where we're going to start to see portions of the network designed for IP ratings and try to make sure that we can protect against ingress and vibration and things along these of this nature, as well as EMI. So you're going to have IP65, IP67, even 69K rated solutions. You're going to have a lot of shielding happening in this space, and you're going to have robust connections that can withstand vibration to your cabinets. You're also more likely to have shorter runs comparatively to the other sections of the network. For this section of the network, the most common type of connector is the M12, which is a barrel style connector. The other thing to consider in this section of the network is that you're typically going to have patch cords that are 600 volt rated for use within a control panel. And this is a safety factor so that you're able to place that cord set nearby to other 600 volt rated cables that are within the cabinet. There is also consideration for network cables as to UL testing. So Panduit, as a manufacturer, we provide those 600 volt rated cables, but we also provide UL 1863 testing, which tests to indicate a 1000 volt dielectric voltage requirement. Okay, so then there's also the cabling that will be put in to cabling subsystem 1 and 2. And this would be the solid construction cabling that would go in more so on the plant floor, but a cabling that you would be likely to see to terminate in the control panel itself. So there can be stranded versions of this cable, there can be solid versions of this cable, it can be shielded or unshielded, and it can have various different types of jackets. It can have a more traditional PVC rating that is an overall good function product. It can be a TPE product, which gives a little higher rating on oil and abrasion resistance and excellent flex capability, or it can be a PUR grade material, which also has oil resistance and is excellent in abrasion and flex. You'll have the same types of considerations, Category 6 versus Category 5E, the type of jacket selection, and whether you're using 2-pair or 4-pair cabling. And then you'll also have the same considerations about 600-volt rating as well. In some environments, oil and gas environments, there are other considerations as well. And this includes some of the DNV, ABS certifications, mud resistance, and the category of performance as well. Okay, so why is structured cabling on the plant floor becoming a best practice? Here's an important factor to consider when following the TIA standards. They follow a cabling practice that's called structured cabling. The concept is to build a cabling system in a systematic way that is predictable, consistent, standards compliant, and easily upgradable. This methodology is universal in commercial buildings, data centers, healthcare, and it exists in industrial plants in the higher levels of the network very often. The increased use of managed industrial network switches is making structured cabling a best practice in the cabinet as well. So it's starting to bring that capability of structured cabling further down into the plant floor networks. You can think of structured cabling as having a good plan for the field installed connections that are going to mate up in the panel. So in this regard, a patch panel in the cabinet is very much like a terminal strip or an interface module that you're using today. It's just your way of landing that field device for the network itself. In the diagram on the right, you can see that structured cabling has what's called a permanent link. That's usually going to line up with the plant cabling or the site cabling where you're putting this panel and this machine. And then you also have patch panels on either end. The left patch panel is likely to be in your control panel, and the patch panel on the right is likely going to be in a data cabinet somewhere higher in the network, and it's going to be located, elsewhere. So you're probably familiar that the overall channel length, as we're indicating on the bottom there, the overall channel length allowable for copper twisted pair is 100 meters or 328 feet. So that's describing something that you're actually probably familiar with. And so together, the permanent link and the patch cords should not exceed this length per the TIA standard. And TIA is what sets that standard. The permanent link cable is often a solid core copper cabling, whereas the patch cords are typically stranded cable to allow for that flexibility in use. It's often where longer runs of stranded cable are used on the plant floor environment, and you need to consider derating factors if you're using long lengths of stranded cable. So following this methodology with structured cabling simplifies the site work, as all the field connections will land in patch panels, and then it's a matter of patching those devices correctly to the network managed switch. So this gives you a little bit of a view of what those field network connections look like in practice. So copper connections can vary from single port connections to 8-port connections and are DIN rail mountable typically for use in panels. This makes it functional. And for considerations with landing fiber, more of that backbone cable that I mentioned earlier, there are different design preferences. Some designers prefer a DIN mountable solution, and some prefer to use boxes that can be wall mounted to house, terminate, and protect the fiber and fiber slack separately away from other components. For Panduit, there are devices specific to fiber and copper. They're all modular jacks, and they all use a common mounting method. So you can switch up exactly what you put in those boxes. Another factor to consider as you're distributing your cable and deciding what cable type to use, it's whether you do factory cord sets or field installed cord sets, or make your own. Although it's common to make the field installed cord sets, there are factors to consider with compliance to the TIA standard. Mistakes, errors, poor installation in the field creates variability in the quality of the connections overall. So it's something you need to consider in your design plan. Our recommendation is to use the factory produced cord sets as much as possible to provide the best assured performance and consistency. Some of the reasons why to consider this, many, or at least some, of factory produced cord sets come pre-tested, at least for the wire map, and some for also the performance of that cord set as well. Some of the cord sets that you will purchase also have QC tracking that can be linked to that testing and traceability should there be an issue in the future. So you can validate those cord sets after the fact. These are all factors you should consider with your Ethernet cord sets and your product selection. Another factor to consider is that a factory-produced cord set will have a much more effective strain relief. Usually has an overmolding, so the strain relief is overmolded to the connector and the cable itself, which provides a much longer length, a much longer life, and a minimal degradation over time. There are definitely cases where you will use field installed cord sets to meet discrete lengths and to make temporary connections when you're troubleshooting, but you should try to minimize these connections to provide the best network consistency. Okay, so there's considerations also in using fiber in place of copper, and this would be probably areas where it's not backbone cabling, but you still want to use fiber in these cases. And there's areas where fiber is more suitable than copper. So when EMI noise is pervasive in that environment, or you know it's pervasive in that panel, it's typically a good reason to turn to fiber, which is totally immune to the EMI issue. Fiber electronics, as well as the fiber connections, are also used to improve the convergence times on your network. If you have many switches, many devices, fiber is often turned to reduce that convergence time on the network. If you're in outdoor applications or you're in a campus environment where many connections are made, fiber gives you that extended range as well to be able to make those connections in another building. Last factor to consider is that there are many fiber solutions out there that are now mechanicals. So they connect mechanically, or they're cammed onto that cable, which makes it so much easier to be consistent and repeatable with this installation. So it's so much easier to install fiber today than it was in the older days with pot and polish. All right, the last factor here to consider on structured cabling is on commissioning and performance validation. So one of the key factors in using structured cabling and following TIA is the ability to test the network and perform the channel testing to better gauge the performance on the network. When we talk, and we often do, about testing to the edge, you can see with this diagram that you can test between each level of the network as the way that it's laid out here, using the structured cabling concept. Each channel represented here by the red circles allows for the validation of the cabling subsystem that we talked about. So cabling subsystem 3 you can test, subsystem 2 you'd be able to test, and then in your control panel and out to those devices you can test with cabling subsystem 1 following this methodology. This is a step that should be done, or is done, ideally right before the commissioning of the cabinet and the machine as it enters service. If you'd like more guidance on this type of testing, you can reference TIA 568C and 568.3-D for copper and for fiber. Although this step is often performed by a low voltage installation contractor, some control systems integrators find the ability to perform this type of testing on their own is helpful in the commissioning stage. Okay, so we're going to do a little review now on selecting media and things to consider when selecting media. So if we look at unshielded twisted pair versus shielded twisted pair, and we also apply some of those concepts that we just learned about M.I.C.E, it's a matter of cost versus a known EMI environment or a known environmental condition. Can I avoid those conditions and reduce costs? Where I can use the UTP. Where I can't, I can apply the STP cable and provide that right level performance and address the EMI. If you recognized in the architecture, I showed you the different segments. Those different segments in the network also provide you the ability to change the type of cabling you're using in each cabling subsystem. You may use a shielded twisted pair at cabling subsystem 1. In cabling subsystem 3, you may not use it. That's part of the advantage of following the architecture. There's also considerations about 5E versus Cat 6 and Cat 6A. From a bandwidth perspective, 5E probably works all day long and is also pretty good at future-proofing that network, right? The other thing to consider, though, is you don't know exactly what's going to be put onto that network in the longer term. Wireless and different other devices, video devices. Category 6A obviously gives you a little more bandwidth from that perspective and a little better future-proofing. The other thing that Category 6A gives you is that higher signal-to-noise ratio. So even though you're still using copper, you can get a little bit better immunity to noise with the higher category rating. So if there's a minimal cost difference, it's probably better choice to go with the higher grade cable. There are a lot of choices around copper and fiber. Some of it is around familiarity with using the fiber, but the other factors are around distance, the distance limitations. It's obviously a longer distance limitation with fiber versus copper. There's also the cost factors. What does the total system cost versus copper? And then the EMI noise factor. When it becomes pervasive, then fiber is a natural choice. There are also considerations around single mode versus multi-mode. This comes down to application. Is it campus-wide that we're talking about? What are the distances that we're talking about? What is the cost of the electronics in the system? And then what is the bandwidth required? The multi-mode solutions can work effectively on the plant floors in comparison to single mode. Okay, so let's talk about one of the key M.I.C.E factors that comes up inside the panel, and that's noise brought into the panel that can couple to your signal cabling and cause performance issues. So these problems can be reduced by applying a layered defense against the noise sources. Good grounding and bonding can help reduce those noise sources. Segregating and separating potential victims from known noise sources can help. And then finally, applying shielding and filtering to control the noise that does get coupled into the circuits. So electrical noise causes field devices to misread the environment. So we've got several examples here of noise sources. VFD drives, servo drives, switching power supplies, even ESD, even lightning. And they can cause equipment damage. They can cause devices to fail, reset, or enter a fault state. And they can result in signal retransmission that causes communication delays. So some of the victims that we typically see are communications wiring, analog signals, high-speed counters and encoders, and controllers and microprocessors. These are typically your noise victims. And typically what we see happen is some business risks that are associated with this. Productivity loss, downtime, maintenance and repair costs, troubleshooting, and unnecessary device replacement costs. We can't trace to where the issue is happening. So if you're supporting equipment with issues around noise, you are aware of it. They're sometimes called ghosts in the machine, and defense in depth is the best approach to try to mitigate those from the start. So if we look at things from a higher level organization standpoint of what you can do with your panel, panel layout and organization is a critical factor to try to reduce that EMI noise mitigation. Step one is to use good layout practice as is recommended by IEEE. Know what your noise sources are and what your victims are likely to be, and figure out your best plan to separate those devices. In the panel we show you, it's actually laid out, and the wiring ducts actually correlate to this. So where your white wiring ducts are, those are your clean pathways. Where you have more of a mixed environment, that's where the gray is, and that's more of what we would call a dirty environment. And then where the black is, that's where your very dirty is, or your cabling that's likely to have noise sources on it. So layout can help you segregate those components and try to give distance between those components. You can use space optimization techniques to help you give you some design flexibility to get to that more ideal design. So we're showing a Panduit solution here with the wiring duct. It can save you up to a 30% in panel space over a traditional wire management solution. So that's one example where you could gain some space. There's other things out there, more compact devices you could use, other types of devices that save space as well. All those can help you have a better layout. And then the final step is around actual noise mitigation devices using a defense in depth approach. So we're talking about safety grounding, but we're also talking about providing a performance ground, implementing braided straps, and creating a ground plane that provides the low resistance path so that any noise wants to couple to that ground plane and come away from your signal cabling. If you're in areas where you do not have space, you can also use shielded devices that can connect to the ground plane and provide you basically a drain that is equivalent to spacing those components apart from one another. And if you have interest after the webinar, you can go out on YouTube and look up Panduit noise mitigation. There's actually a demo out there showing a shielded barrier. When it is connected to the ground plane, in this demonstration, you can see wire segregation and the effectiveness at reducing noise, and also shielded barriers providing that same level of noise mitigation as well. Okay, so I talked earlier about having safe access. So we're more likely to have IT personnel and personnel that may not be as familiar with safety and PPE requirements that need access to this equipment at some point. It could be routine maintenance, it could be some kind of firmware update, it could be a call that comes in the middle of the night, I suppose. These data access ports that are available are a method to provide that routine access and maintenance with a closed door on the enclosure. So these can be full data access ports with power and with multiple ports for connecting devices inside the panel, or they can be single port connections that can provide the connectivity through the panel and maintain the IP and NEMA ratings of the enclosure. So this is something to consider from a safety perspective, setting up that panel so that as much closed door access as possible for those routine tasks. So the final factor we'll consider in the connected cabinet is having a defense in depth strategy around security. From an overall perspective, every plant floor should have some type of security strategy today. So what we're showing you there on the left for reference is the approach that's recommended from IEC 62443, and it is a multi-layer security approach, from the device level to the application to the computer to the network to the physical deployment and to the policies, procedures, and awareness. We want to make you aware that in your designs, as you're putting this network equipment into the control panel, there are physical steps that you can take to help lock down that enclosure and help lock down the ports that are inside that enclosure, be they on the switch with RJ45 connections, be they in a more data center environment where you have fiber connections, or be they with a PLC or other device that might have a USB connection. There are physical port blockouts and physical port lock-in devices that can help you either maintain the connection that you don't want moved, that you don't want people messing with or moving around, or that will block out a port to give you additional protection. Just in case somebody didn't turn off that additional port, you can block that port out as well. So these types of devices, very simple to implement, but they prevent that network access by unauthorized personnel and unauthorized devices that they may try to plug in to that network. So this is a simple thing that you can add to your security strategy that can help you be effective. Okay, so I've talked quite a bit about standards around the physical network throughout today's presentations. So here is a slide that gives you some of the good references for you when you're evaluating all three of the cabling subsystems that we talked about. So I touched on many of these, obviously, but there are certain other areas that we didn't hit in depth, things like cooling and things like grounding and bonding that we obviously are topics on their own that you will need to investigate further to build your physical network strategy. But these standards listed here are a very good starting point when you're evaluating the different factors supporting the network in your control panel design and in the plant floor network itself. So I hope you've all gotten something out of the presentation today. There's many things I talked about in terms of structured cabling, in terms of TIA and the M.I.C.E factors, and there's some certain spot solutions I talked about as well. There are 4 different resources that we recommend. If you found any of those things that I talked about interesting today, there are resources available to you on panduit.com. We will also make them available to you as we follow up after this webinar. So there is a smart control panel brochure that highlights solutions that fit in that cabling subsystem 1 and in the connected control cabinet. There is a preferred parts catalog that helps you narrow it down into the industrial application and what products apply. There is a M.I.C.E selection guide, which is very helpful in applying the M.I.C.E techniques in the different cabling subsystems. And then there's also a wiring duct selection guide. So if you're looking at that space optimization, that guide could help you as well. And so that's the end of the presentation portion. We're going to see if we have any questions from the audience right now.
Yeah, thanks, Mike. We'll use this time to answer questions. Please feel free to submit your questions utilizing the chat box on the GoToWebinar app. We will answer as many questions today as possible. Give them just a minute or two to type some questions here. Okay, it actually looks like we have our first question here. I'm used to point-to-point connections. Who benefits from going to structured approach with patch panels?
Okay, that's a very good question. So who benefits the most from a structured cabling approach is the person who supports the network or the group that supports the network. So if that's an end user, that, as we described in the presentation, the structured cabling approach gives you that upgradability, gives you that predictability in the network, and makes it easier to troubleshoot the network as well. So if you are the company supporting that network, you are going to directly benefit in supporting that panel and supporting that machine that's out there on the plant floor by using that structured cabling approach. Now, there's absolutely going to be places where point-to-point cabling is the right choice to make because you just can't apply structured cabling everywhere. But you will still be able to support both point-to-point and structured cabling in your approach.
Looks like we actually have a couple more come in here. The next question, Mike, is who does the type of channel testing on the network installations mentioned in your presentation?
Right. So I mentioned it just briefly in the commissioning slide where I was talking about the actual testing of the network itself. Typically, the cabling and connectivity on the plant floor, or what I refer to as the site cabling, is put in by a low voltage installation contractor. So this is could be electrical contractor, but most likely going to be a low voltage contractor or one that does both that will install this type of cabling. Sometimes an end customer has a preference for who does that. It's typically that contractor who validates the system. So they'll validate layer 2 usually on that network for the end customer. There are scenarios, though, where you may want to have the capability to do that same type of validation. If that's an area of interest for you, Panduit actually has training in order to be able to do that type of testing. And the other thing to consider there as well is your coordination with the contractors that are going to be on site. If there is also a plant cabling installation, you'll want to be in contact with that contractor so that you can coordinate your machine connectivity with the overall plant floor connectivity.
Looks like we have one more here. How do M.I.C.E. and environmental factors apply in the control panel? Control cabinet?
Yep, same thing. So M.I.C.E. factors, the ones that we described, right? It's M.I.C.E., so mechanical, ingress, climate and chemical, and electromagnetic noise. All of those factors can come into play in the control panel. It's just the fact that we're using this acronym. So obviously noise is one of the biggest factors because you're pulling all these devices, all these terminations together in that control panel. You've got that increase in network devices, which can be more of those noise victims in the control panel. And we need to plan for how we're going to address noise mitigation and EMI primarily, but obviously all the other factors come into play. There's a lot of vibration on the plant floor. There's vibration nearby to where this control panel would be. If we're using standard office grade connections, we are at risk of losing that connection. That's where we have a solution that addresses that M.I.C.E. factor for vibration. Ingress. So enclosures are designed for ingress protection, NEMA rating. So are the connectors. We need to use the right connectors that attach to that enclosure and maintain its NEMA rating. So across the board, M.I.C.E. applies in the control cabinet.
Okay. Looks like we don't have any more questions at this point. I wanted to thank everyone for their time today and for the questions. This will conclude today's webinar.
All right. I want to thank you all for your time, and I hope you find that smooth road ahead of you, and if we can help you in any way, we're here to do it. Thank you all.
Mike.